Hello, beta. Good afternoon, everyone.
Good afternoon, sir.
Good afternoon. Beta, the recording of the class is on. So let's continue with our topic for today. Today we are going to start off with the basics of celestial navigation. Basically the familiarization with the almanac, what all items are given there. Then moving on to altitude correction and maybe amplitude and azimuth, whatever is possible today. So that's what we are going to do now. Once we are familiar with the almanac, with the altitude correction, calculation of the azimuth and amplitude, we will be ready to go into the site solving methods. So that's the plan going ahead. We will do site solving methods. Then next after site solving, we will do the plotting. So if you have almanacs with you, just keep them close by. You can refer to the almanac, open up the pages and refer to the almanac as I explain what all items are there in it. So keep the almanacs with you and we start off with today's presentation. Any doubts in your mind before we start off?
सर ये एक स्टार आइडेंटिफिकेशन वाले में था जो एक्सरसाइज 30 है सर, ये प्रैक्टिकल नेविगेशन का। उसमें सर लाइक पहले 4 क्वेश्चंस में उन्होंने जो क्रोनोमीटर का एरर दिया है वो स्पेसिफाई किया है, फास्ट है या स्लो है, सो वी कैन इजीली प्लस माइनस। बट जो लास्ट क्वेश्चन है सर उसमें जस्ट एरर मेंशन किया हुआ है, तो इसमें ऐड करना है या सब्ट्रैक्ट करना है, ये कैसे पता चलेगा सर?
Beta, this is the last question. Huh? Okay, let me open up. Just give me a minute.
क्वेश्चन नंबर 5 एक्सरसाइज 30।
Just give me a minute. What's the page number, beta?
सर 192।
Okay. Beta, that's a misprint. They should have told you whether it is slow or fast. Without that, you cannot find out. So let me show you here also.
ओके सर।
Okay, so what you do is just go to the answers and in the answer you can see what time have they taken. I think it is fast, so they have subtracted it. Straight away pick up the GMT from the answer and solve the question.
ठीक है सर, ओके, थैंक यू।
Okay, that's a misprint. They need to tell you whether it is slow or fast. Okay, so shall we proceed ahead with the presentation?
यस सर।
Okay, all right. Let's set up the presentation. So we will first see what is the concept of site solving, what we actually do in site solving, the basic concept. Then we move on to the altitude correction and then the almanac familiarization. So that's what we are going to do. So let's continue. In this presentation on celestial navigation, we are going to learn about the concepts related to site solving, celestial site solving. Now we are aware that the most basic job of a navigator is to take his ship from position A to position B, from his departure position to his destination position. Now, the first and foremost requirement of taking your ship from point A to point B is the preparation of a passage plan. This passage plan is prepared with the help of sailing methods, because for passage planning, we need to know what are the courses which the ship needs to steer and what are the distances which the ship needs to steam. And these courses and distances are calculated using different sailings. There are total 5 sailings which are there. We have rumbline sailings, which are parallel sailing, plain sailing, and Mercator sailing. And then we have great circle sailing and composite sailing. So with all these methods, navigator can easily plan his passage. He can find out what all courses and distances the ship needs to steam. Now, once this job of passage planning is done, the next thing on the line is the execution of this passage plan. The ship has to actually move on the plan which has been prepared. Now, when the ship starts its passage, the second most important job for the navigator is to monitor the vessel's progress on the intended track. We have to continuously monitor the progress of the ship on the track. An integral part of this monitoring is position fixing. So we have to fix the ship's position at regular intervals to determine whether we are following the planned track or the ship has gone off track. It has to be continuously done. Now, this position fixing is very, very easy and simple in today's world. We have the satellite position fixing available to us. We have the GPS or the GLONASS. There are a lot of systems which are also coming up now. But in these concepts which we are going to discuss, we will assume that the satellite position fixing is not available to us. And we will try to fix up the position of the ship on methods which are independent of these celestial navigation, independent of the satellite position fixing systems. Now, without the GPS position fixing, as you depart from the port, you still have the terrestrial navigational aids, land-based objects visible to you. You can see the lighthouses, you can see the coastline, you can identify the features of the coastline, and you can fix your position using these terrestrial objects. An observation of a lighthouse can give you a bearing, a position line. The range of a lighthouse taken with the help of a radar can give you a position circle. And you can plot these on the chart and fix up the position of the ship. But as we go away from the land and we move into open sea, the terrestrial objects are not available to us. They are no more available. The vessel has moved into open sea, where these terrestrial objects, the coastline, the radars, the lighthouses, beacons, buoys, all these objects have gone outside our view. So we cannot use them for position fixing. Now this is where celestial navigation comes to our rescue. Now we have many celestial objects. By celestial objects, we mean the objects which we see in the sky. Basically, they can be divided into four categories. We have the sun, we have the moon, we have the planets. There are four planets which are used for celestial navigation: the Venus, Mars, Jupiter, and Saturn. These four planets are closer to us as compared to others, and they are easier to identify in the sky. So these are the ones which we use for our navigation or position fixing. And the fourth category are the stars. So sun, moon, planets, and the stars. All these heavenly bodies are known as celestial objects. So when we go into open sea, terrestrial objects, lighthouses, navets are not available to us. The celestial objects are visible all the time. We can see the celestial object. The sun is available to us during the day. Moon could be available during day as well as night. Planets and stars are available to us during night time and in twilight times. So each of these celestial objects can act as a lighthouse in the sky, and we can use each and every object, each and every celestial object for our position fixing. Exactly as a lighthouse on land gave us a position line, we were able to plot that position line, combine it with another position line or a position circle, and fix up the position of the ship. Exactly in the same way, all these celestial objects can provide us with position lines or position circles. Every single celestial object at a particular time can provide us one single position line. If you take sight of two celestial objects, you get two position lines, and with these two position lines, you can easily fix up the position of the ship. So we will now understand how can we fix up the position of the ship, or how can we obtain the celestial position line. Now these are obtained by what we call as sights, solving the sights. So we will see how the sights are taken, how the sights are solved, position lines obtained, and the position of the vessel fixed up. Now the first thing to understand regarding celestial position fixing is that celestial position fixing is slightly complicated and time taking as compared to terrestrial position fixing. Terrestrial position fixing is very quick and easy. If you observe a lighthouse, you take a bearing of that lighthouse, plot that bearing on your chart, and you have the PL. It is not so easy with the celestial objects. Celestial position fixing is complicated. Now, why is it so? Why is it complicated? It is basically due to two reasons. One is the amount of distance involved between us and the celestial object. The nearest celestial object which we have is the moon. Then next in the line comes some of the planets. Then comes the sun. Then come the remaining planets. And the farthest objects which we have for celestial navigation are the stars. The distances involved are very huge as compared to the distances involved with terrestrial objects. Terrestrial objects, the lighthouses on the ground, were within our visibility range, 10, 20, 30, 40, 50 miles at the most. But these celestial objects are from thousands of miles to light years away from us. So because of this huge distance, position fixing becomes, or obtaining position lines becomes little tricky. The second thing why the celestial navigation is complicated, finding position lines is complicated using celestial object, is because of the relative motion. The Earth, we are aware that Earth rotates on its axis from west to east. Now, because of this rotation of the Earth, Earth completes one complete rotation in one day, 24 hours. Because of the rotation of the Earth, all celestial bodies appear to move exactly in the opposite direction, rising on the eastern horizon, crossing our meridian at a particular time, and then setting on the western horizon. Now, this is the apparent motion of the celestial bodies. It is not that the sun, moon, stars, and planet are actually moving that way in the sky as they appear to us. The stars are fixed objects in the sky, the celestial sphere or the space or the universe. The sun is more or less practically fixed up. So, but still they appear to move to us. It is because of the relative motion due to the rotation of the earth. So these two things make celestial position line little tricky. Now we are going to understand how do we fix up our position using the celestial object. Now for this, what we need is the true altitude of a celestial body. So if you want to obtain a position line from a celestial body at any particular time, you need to have the true altitude of that celestial body. Now using this true altitude along with the almanac information of the body, the information given in the almanac is basically the GHA and declination. Greenwich hour angle and declination of each of these celestial bodies is provided to us in the almanac. Using that data and using the true altitude of the body, we can obtain one position line from one celestial body at one particular time. So this is the concept of position fixing using the celestial objects known as sight solving. Now there are total 5 different methods which are available to us, can be used in different scenarios, different conditions to fix up the position of the ship. The first one and the simplest one is the latitude by meridian altitude, also known as MARPAS. Second one, longitude by chronometer. Third, intercept. Fourth, X meridian method. And number 5, Polaris or pole star observation. So these are the 5 different methods which we have, can be used with different bodies at different times, and they help us to obtain position lines from celestial objects, heavenly bodies, the sun, the stars, planets, and the moon. Now, before we go into sight solving using these celestial bodies, we need to be clear about some basic concepts of celestial navigation. What are these basic concepts? The first concept is of altitude correction. What is this altitude correction? Now, as I told you before in the previous slide, that to obtain a position line from any celestial body, we need to know what is its true altitude. Now, to obtain the true altitude of a body, the instrument which is available to us is the sextant. The sextant is an instrument which can be used to measure angle between any two objects which are visible to us. So if two objects are visible to you, you can use the sextant and you can obtain the angle between those two objects. So the altitude is also measured as an arc or as an angle. So it can be measured using the sextant. Now, the true altitude is basically the arc of the vertical circle or the angle at the center of the earth contained between the rational horizon and the celestial body. Now, when we use the sextant to obtain the altitude of a body, one, we are not at the center of the earth, we are on the surface of earth. The angle is measured not at the center of the earth, but at eye of the observer. And second, uh, sextant can measure the altitude between two visible objects. Now the horizon, what is visible to us, is what we call as visible horizon. And the horizon which is used for true altitude is rational horizon. So the angle which we obtain from the sextant is not the true altitude of the body, it is the sextant altitude of the body because of these two reasons. One, we are not measuring the angle at the center of the earth, we are measuring it at the eye of the observer. So it will be different from true altitude. And second, we are not using the rational horizon because we cannot see the rational horizon. We are using the visible horizon to measure the angle, and because of it, the altitude which the sextant gives us will be different from the true altitude of the body. Now the altitude which the sextant gives us is known as sextant altitude. It has to be corrected to obtain the true altitude of the body. That is the concept of altitude correction. So we will be now refreshing up the altitude correction. The second thing which we need to be familiar with for solving these celestial navigation problems is the familiarization with the almanac information, the information which the almanac, the nautical almanac, provides us. The third thing which we should be clear about is the chronometer ambiguity. Now, chronometer is a special clock, a highly accurate clock, which is used for obtaining the GMT. The use of chronometer has become redundant nowadays, but sometimes or the other, it often gets into the questions which come in our papers. So it will be good if we understand what is this chronometer ambiguity and how it is resolved. Practically, it is not of much use nowadays because we have access to accurate GMT time now, and chronometer is hardly used to obtain the GMT time. The next concept which we need to be clear about is how to calculate the azimuth of a celestial body. Azimuth basically means the direction or the bearing in which the body is. We can calculate the azimuth of a celestial body using the almanac information and the concept of calculation of the amplitude of a celestial body. Now, amplitude can be easily explained as the bearing or the azimuth of the body when it is on our rational horizon, or you can say when it is rising or setting. So these are the concepts which we need to be clear with before we proceed on to site solving. So we are going to refresh all these concepts one by one, and then we will be proceeding into solving of sites. We have already seen the celestial sphere, so let's skip this one. Let's go to altitude correction straight away. Now, the first basic concept which we are going to see is the altitude correction. So as I told you before, the altitude what we obtain from the sextant is the sextant altitude, and the altitude what we require for our site solving purpose is the true altitude. So altitude correction is the process of correcting the sextant altitude to obtain the true altitude of a celestial body. So let us see now what all corrections are applied to the sextant altitude to obtain the true altitude. So we obtain the sextant altitude of the body using the sextant, the first correction which we need to apply to this sextant altitude is the index error. Now, what is this index error? This index error is basically the error of the instrument. Now, the sextant is a very complex equipment, having very sensitive equipment and very precise equipment. There are a lot of moving parts in the sextant, and because of those moving parts, there is a scope and there is a chance that those moving parts may be disturbed from their original locations, giving rise to some errors. These errors are basically the errors of the instrument. So this instrument error of the sextant is known as the index error. Now, as far as our MMD questions are concerned, this index error is provided to us in the question itself, and we need to apply it to the sextant altitude. Now, how is the index error applied? The index error is defined as either on the arc or off the arc. Now, if it is mentioned to be on the arc, the index error should be negative. So you can see here in the explanation, if the index error is on, that means the correction is negative. And if the index error is off the arc, that means the correction is positive. Now you can easily memorize it and remember it in terms of a light switch. Consider the index error as a light switch. If the switch is on, you put it off. If the switch is on, you put it off. Putting it off means negative or subtracted. And if the switch is off, you put it on. Putting it on means it is to be added or the correction is positive. So index error, the error of the instrument, it is negative if it is on the arc, and it is positive if it is off the arc. Now, once you apply the index error, the altitude what you obtain is the observed altitude of the celestial body. The next correction which we apply to the observed altitude is the dip correction. Now this dip correction is based on the height of eye of the observer. This is based on height of eye, and this dip correction is always negative. The dip correction is always negative, and it is based on the height of eye of the observer. Now, where do we obtain this dip correction? I will show you the dip correction in the later slides. In the coming slides, I'll show you the dip correction is obtained from the dip correction table given in the nautical almanac. So this is the second correction which we have applied. Once we apply the dip correction, we obtain the apparent altitude of the celestial body. Now to the apparent altitude, we have to apply 3 more corrections. The first one among them is the refraction correction. The refraction correction is basically due to the refraction of the light through the atmosphere. Whenever we see a celestial body, we are able to see it because some light from that celestial body is able to reach to our eyes. So that light obviously has to pass through the atmosphere. All the celestial bodies are in space. So any light coming from a celestial body to our eye has to pass through the atmosphere. Now when it passes through the atmosphere, it undergoes what we call as refraction. The ray of light coming from the celestial body suffers refraction or undergoes refraction. Refraction is a physics principle which says that whenever the light passes through 2 different mediums having different densities, it will either bend towards the normal or away from the normal. depending upon the densities. So when the light is traveling in space, that is one medium, the density is 0. And from space, it enters into the atmosphere. Now, atmosphere has some positive density, so the light bends towards the normal. Now, this refraction correction is always negative. Because of refraction, the celestial bodies appear slightly higher than where they actually are. So this correction is always negative. The second correction applied to the apparent altitude is known as the semi-diameter correction. Now, what is this semi-diameter? The true altitude of a body is measured with reference to the center of the celestial body. Now, stars as well as planets, they appear to our eye as point objects. So when you take their altitude, you are automatically taking the altitude of the center of the celestial body. But that is not the case with the sun and the moon. Sun and moon do not appear as point objects. In fact, they appear as disks. So now the center of the disk is not visible to us. It would be very good if there is a dot in the center of sun and moon and we can directly measure the altitude up to that center, but that's not the case. So we are not able to identify the center of the sun and moon using our eye. So what we do in the case of sun and moon is we either take the altitude of the lower part of the disk of the sun or the moon, or we take the altitude of the upper edge of the disk. Now this is also known as lower limb or upper limb. Now when you take the altitude of the lower limb, obviously to reach up to the center of the body, you will have to add the radius of the body as visible to you. Now this radius in terms of altitude correction is known as semi-diameter. We know diameter upon 2 is what the radius is. So in navigation terms, it's not called as the radius, it is called as the semi-diameter. So the semi-diameter correction for lower limb will obviously be positive because from the lower limb, you have to reach up to the center of the body, so you have to add the semi-diameter. And if you take the observation of the upper limb, then this semi-diameter correction will be negative because from the upper limb you need to come down to the center of the body by an amount equal to the radius or the semi-diameter of the disk of the moon or the sun. So this semi-diameter correction is applicable only in the case of sun and the moon. There is no semi-diameter correction in case of stars and planets.
Yes, sir.
Now the third correction which we apply to the apparent altitude is the parallax correction. Now parallax is the angle at the center of the celestial body subtended by the radius of the earth. That is what we call as parallax. And this parallax correction is always positive. So you can remember P with parallax, P with positive. So parallax correction is always positive. Parallax is the angle at the center of the celestial body subtended by the radius of the earth. So these are the three corrections which are applied to the apparent altitude. Refraction, always negative. Semi-diameter, positive in case of lower limb, negative in case of upper limb. And the parallax correction, which is always positive. Once you apply these three corrections to the apparent altitude of the body, what you obtain is the true altitude of the body. Now, the three corrections which we saw to be applied to the apparent altitude, refraction, semi-diameter, and parallax, these ones, They can be easily applied as a single correction. We do not need to apply them separately, one by one. That would be unnecessarily lengthy, cumbersome, and more time taking. We can apply all these three corrections in a single correction, and they are available to us in the nautical almanac. So when you apply all these three corrections using a single correction, it is known as total correction. Now, total correction can be easily obtained from the almanac, and it consists of all these three corrections in it. That is refraction, semi-diameter, as well as parallax. So the total correction gives us a very quick and easy method to correct the altitude of a celestial body. The individual correction methods are usually referred to or used during your pre-C training, because that's when you need to be clear about the concepts. But once you come to second mates or phase 1 level, the individual correction method is not usually recommended. The questions can be easily solved using the total correction obtained from the nautical almanac. So this is the complete altitude correction process. We start with the sextant altitude. First correction is the index error. It is negative if it is on the arc, and it is positive if it is off the arc. The second correction is after applying the index error, we obtain the observed altitude of the body. The second correction which is applied is dip correction based on height of eye and is always negative. Then we obtain the apparent altitude. The three corrections applied to apparent altitude are refraction, which is always negative, semi-diameter, which is positive for the lower limb, negative for the upper limb, applicable only in the case of sun and the moon, and the parallax, which is always positive. All these three can be combined together in one single correction, that is the total correction. Once applied, they give us the true altitude of the body. Now this is the true altitude which we require for the purpose of sight solving. Let us now see one by one how do we obtain these corrections. The first one which we applied was the index error, which I told you that the index error is given to us in the question itself. The value is picked up from there and applied. The second correction which is applied is the dip correction. The dip correction is obtained from the nautical almanac. If you open your nautical almanac, the first page of the nautical almanac looks like this. You have the first page of the nautical almanac. And on this page, the table which you see on the right hand side, the one which is highlighted now, this is the dip correction table. So you can see in this table, the height of eye is given in meters as well as feet, though feet is very rarely used nowadays. So the height of eye is given in meters as well as feet, and against the height of eye, you can see the value of the dip correction. So the dip corrections are tabulated here. There is a minus sign in front of all these corrections, reminding you that the dip correction is always negative. So you see a range of the height of eye. Let us say you see a range from 6.6 to 6.9 meters. And within this range, the value of dip correction to be applied is minus 4.6 minutes. Now, in case you have the height of eye falling at a critical entry means an entry which exactly matches with the table entry. Let us say 6.9. So in this case, there could be a doubt whether we should pick up minus 4.6 or minus 4.7. So out of these two, any value can be picked up. The difference will be only 0.1 minutes, which is a acceptable difference. But as per the convention, we pick up the upper value, the value which is upper in the table. So for 6.9, you can pick up minus 4.6 minutes. So this is the dip correction table. Now, after the dip correction, the next correction which we require is the total correction. So let us now see the total correction for all celestial bodies one by one. As I told you, we have 4 celestial objects, celestial bodies available to us. That is the sun, the stars, the planets, and the moon. So let's open up the first page of the almanac once again, the same page which we saw in the previous slide. Now you can see the total correction for the sun. Let's first find out it for sun. You can see the total correction for the sun given on the left hand side in the first table. So you see the table which is highlighted. It gives you the total correction for the sun. The table is entered with apparent altitude as well as the limb of the sun. So you enter with the apparent altitude. There are 2 corrections given against each apparent altitude, or for a range of apparent altitudes, 2 corrections are given. The first correction is for the lower limb of the sun, and you can see a positive sign in front of it. And the second column gives you the correction for the upper limb of the sun. You can see a negative sign for the upper limb total correction. Now, one more thing which you will observe here is that the total correction table of the sun is divided into 2 parts. The first part of the table gives you the total correction for the period between October to March. And the second part of the table gives you the correction between April to September. So basis the date on which you have taken the site, you will be entering the appropriate part of the total correction table. Check the date for which what is given in the question on which the site is taken, and basis that date you enter into the appropriate part. Enter with apparent altitude. Out of these 2 corrections, pick up the correction for the limb which is given in the question. Lower limb corrections are positive, upper limb corrections are negative. Now moving to the second celestial body, that is the stars, and the next one, that is the planets. Now for stars and planets, we have a single table. The second table which you see on the first page of the almanac gives you the total correction for stars as well as planets. This table is also entered with apparent altitude. So you enter with the apparent altitude, and for a range of apparent altitude, the total correction value is given here. All the total correction values are negative. So the second table gives you the total correction for stars as well as planets. Now, when you are picking up the total correction for planets, you have to be careful about 2 planets, that is Venus and Mars. Now, whenever the altitude correction is being done for Venus and Mars, once you have referred to the total correction table, obtained the total correction against the apparent altitude, after that you have to apply an additional correction also. you see the additional correction value is mentioned here in the second part of the table. This additional correction also has to be applied to these two planets, that is Venus and Mars. Now, how is this correction applied? You can see for every planet, say for Venus, they will give you a range of dates. In the first part, they have given January 1 to December 10. The apparent altitude between 0 to 60, the correction is plus 0.1 minutes. Then in the second part, they say December 11 to December 31. From 0 to 41 degree apparent altitude, the correction is plus 0.2. For 41 to 76 degree apparent altitude, the correction is plus 0.1 minutes. So the correction has to be picked up from the second part of the table, the additional correction, and the additional correction has to be applied in addition to the total correction obtained from the total correction table against the apparent altitude of the body. Now, important thing to understand here is this additional correction, as is clear from the name, is additional to the normal correction. The normal correction given on the left-hand side part of the table against a range of apparent altitudes. The additional correction is over and above the normal correction. Please don't forget to apply the normal correction. It should not happen that you apply only the additional correction and you forget about the main correction. So it is applicable only in the case of Venus and Mars. Now a doubt may arise in your mind. What is this additional correction for? Now basically Venus and Mars are closer to us compared to Jupiter and Saturn, which are the other two planets used for celestial navigation. Being closer to us, they appear slightly bigger, and just like Moon, it is possible that they may be showing phases. You may not be able to see the complete planet, but you may be able to see some part of the planet, just like you can see the phases of the Moon. Sometime you see the full moon, sometime you see a gibbous moon, sometime a crescent moon. So that way there could be this phase effect with these two planets also. And other than the phase effect, these planets are very close to us. So they have a substantial parallax, which is a positive correction. The parallax of these planets could also be substantial. There is no parallax for Jupiter and Saturn. They are too far away from us. So the radius of the Earth does not subtend a suitable angle. But for Venus and Mars, there could be a little bit of parallax. So this additional correction takes care of both these small corrections, that is the phase correction and the parallax correction. These are not applicable to Jupiter and Saturn as they are far away, they do not show the phases, and they do not have any parallax. They are not applicable to the stars either, because stars have their own light, they emit their own light, so they don't show any phases. And secondly, stars are so far away that parallax for stars is nil. So this was the total correction for the Sun, for the stars, and for the planets. Beta, any doubts up to here? Hope everything is refreshed.
Yes, sir.
Okay. So to nahi gaya beta?
Sir, no, sir.
Okay. I hope everybody is awake. Okay, all right. So beta, we are almost done for our first session. So let's stop here. Next lecture when I meet with you, I don't have a session with you on Saturday, I believe. Then next lecture when I meet with you, we will cover up the remaining familiarization with the almanac, and then we will move on to our first side solving method, Marpas, and then after that long by Cron. So over the weekend, I would request you guys to get familiar with the almanac if you have not already done so. Try some ABC calculations, azimuth, calculation of azimuth, and calculation of the amplitude. You can practice a couple of questions, and I will revise them quickly in the next session also, so that we are ready to jump into side solving methods. So once we are all ready, then we will be doing these 5 methods one by one. Go ahead, Arun beta.
सर जो ये लास्ट क्लास में जो स्टार आइडेंटिफिकेशन वाला कराया था उसका एक बार स्लाइड दिखा देंगे, बिकॉज मैं जो कर रहा हूँ कैलकुलेशन उसके हिसाब से जो एसएचए और डिक्लिनेशन आ रहा है वो कहीं भी मैच नहीं कर रहा। बाकी ये जो 30 एक्सरसाइज के हैं वो सब सही आए हैं।
Are you talking about the question which I gave you?
Yes sir, yes sir.
Oh, don't worry beta, that question was made up just to explain the concept, so SHA declination will not match.
तो काफी कंफ्यूज हो गया सर, मैं बिल्कुल बहुत दूर दूर तक कुछ है ही नहीं उसके बाद।
Okay, no problem बेटा, don't worry. वो मैंने सिर्फ आपको कॉन्सेप्ट समझाने के लिए खुद ही बनाया था क्वेश्चन, so it was not a real question. Okay. You can, if you want, you can practice the questions from the star identification in the practical navigation book. So there you will find the answers.
Okay sir, thank you.
Okay.
सर एक्सरसाइज ही नहीं मिल रही, जस्ट स्टार आइडेंटिफिकेशन मिली तो
नहीं मिली बेटा? लो
No,
अभी
sir.
मिला देते हैं, अभी मिला देते हैं बेटा. ये लो बेटा, practical navigation chapter 21 star identification, and you will see one worked example, and after that the exercise.
ओके सर, थैंक यू सर। ये शायद नई वाली बुक में नहीं है, पुरानी वाली बुक में है।
It is not there at all. The chapter number may be different, but should be there beta.
ओके सर, आई विल चेक अगेन।
Okay, just check. The name should be star identification.
पुरानी बुक में पेज 188।
Yeah, that's right. Okay. So that's all for this session beta. Wish you a happy Dashera. Enjoy your weekend.
थैंक्स कैप्टन, यू टू।
सर वो टाइम जोन टाइम वाली शीट आप डाल दीजिएगा सर ग्रुप पे।
Oh, I forgot. I'll put it now. Don't worry, I'll put it.
ओके ओके, थैंक यू सर।
सर सैटरडे को क्लास है, उसको ऑफ कर सकते हैं क्या?
बेटा अगर ऑफ करेंगे ना तो आवर्स में थोड़ी सी दिक्कत आ जाएगी. वी विल हैव टू वर्क ऑन सम अदर सैटरडे.
नहीं सर, जैसे रोज जितनी क्लासेस हैं उसका आधा आधा घंटा या कोई जैसे एक एक आधा आधा घंटा डेली करके अगर वैसे एडजस्ट कर सके तो हमारा सैटरडे ऑफ हो जाए तो।
इट विल बिकम टू कॉम्प्लिकेटेड. आधा आधा घंटा करते करते 6 घंटे कवर करने के लिए 2 हफ्ते लग जाएंगे बेटा.
सर है टाइम तो, अगर आप चाहो तो हमारा
फ्राइडे को लगा लो सर क्लास,
या कल आप 2 घंटे लगा लो चाहे से, हमें तो कल भी कोई इशू नहीं है।
टुमारो बेटा अगर मेरी क्लास होती तो मैं लगा देता, बट आई अनफॉर्चुनेटली आई डोंट हैव द क्लास विद यू. जस्ट रिक्वेस्ट द अदर फैकल्टी मेंबर्स.
We requested, but they said it's all depend on the course coordinator. They cannot do anything. So मैंने फिर कहा मैं आपसे ही पूछ लूँगा.
Now for the course coordinator it all depends upon completing the hours. So I'll run short of the total hours बेटा.
ठीक है सर, फिर चलने देते हैं।
फिर तो चलने देता है सर.
Yeah, let it go on autopilot.
समझ गए सर हम।
Okay, all right. So ठीक है बेटा, then we call it off for today. See you in the next session. Bye bye.
थैंक यू सर।
थैंक यू सर, सेम टू यू सर।
Okay, thank you.